which I just contract the indices. So if I make something like the Riemann tensor or the Ricci tensor, and then contract with the metric to get some scalar like the Ricci scalar, that is of course invariant under the SL2R subgroup, but it will not be invariant under the full SLNR gauge transformation. So diffeomorphism, since SL2R is only a not necessarily invariant under the full gauge symmetry. So that's that makes life more complicated, makes it more difficult to sort of to disentangle what are the gauge invariant notions. So that's why our geometric inclusion starts failing when you look at these higher spin theories. Earlier you could say in an invariant sense whether there was a singularity because the metric of the let's say if the Ricci scalar or some other curvature scalars blow up, you can say that there's a singularity there because that's a diffeomorphism or net invariant characterization. But if you have this much bigger symmetry, then it's more difficult to so you might be misled by just computing some curvature scalars in such a theory that there is a singularity, because it may be that that's just a gauge artifact. Maybe just like coordinate singularities, we now understand our gauge artifacts in, say, the Schwarzschild metric, etc. So similarly, even curvature singularities in such a big theory might be gauge artifacts. And this is, you can actually see explicit examples of this in the case of solutions of such theories, even in 3 dimensions. You can construct black hole-like solutions. The notion of horizon, the notion of singularity, these things are much more subtle, and you have to phrase them now in purely gauge theoretic terms, which is one reason why I talked about this Gibbons-Hawking procedure in the language of holonomies, because here in this Chern-Simons formulation, that is the language we will be sort of forced to employ to know what is gauge invariant. So this is an important point that diffeomorphism invariant observables are not necessarily gauge invariant observables from the point of view of this larger gauge symmetry. Okay, any questions? So this was sort of kinematical in the sense that I so far just talked about the SLNR gauge field and its spin content. I explained to you why you have fields of spin S all the way up to n, spin n, and how the gauge transformation parameters at least correspond to the gauge parameters that I described to you earlier. But all this just follows from thinking of these as gauge fields. But now, let me say a little bit about the dynamics. So the dynamics is given by the Chern-Simons action. So the equations of motion of these gauge fields is still still given by flat connections. So I should call it just f of a. Tilde equal to 0, where this f of a is again dA plus a wedge a, and similarly for a tilde. But I didn't put this a index because now these are elements of, these belong to SLN R. So, because this gauge field belongs to SLN R, so you can expand this f of a also into fa of a dA plus. Up to it, So the statement that this is 0 is the statement that each of these components are 0. So this equal to 0 implies that each of these are now 0, and so those give you sets of coupled equations for these omegas, these generalized field binds, and so if you combine these two equations, so you see that for each spin, there's one set of equations, so you get as many equations as there are unknowns, namely these omegas and these e's, these generalized field binds and spin connections. So so one gets, so one can, so there are now generalized torsion equations. Which determine which determine omega a1 to as minus 1 in terms of the e's, the whole set of e's, the generalized field bind, and there are generalized curvature equations. Which determine then the field bind. So these are the, remember we had dE plus omega wedge E equal to 0. So these are, so this was what allowed you to determine omega in terms of E. So you will have these kinds of equations. For instance, if you take you just need to read off the piece corresponding to spin s minus the spin s minus 1, the piece with ta1 to as minus 1. You setting that component equal to 0 and taking the difference with the the similar one for the a tilde will give you an equation for d a1 to as minus 1 and enable you to write that in terms of, so it will be a more complicated set of equations than this, but in principle, there are algebraic equations that enable you to solve for the omegas in terms of the e's. So, yeah. And then there are the generalized curvature equations, which are like d omega plus omega equal to 0. Well, not equal to 0 in the case of ADS3. This is proportional to. So you have generalizations of these. So, so now it won't take as simple a form as this, but just it takes this form if you write in terms of the full SLNR omega and the SLNR E, but in terms of individual ones, it will be all coupled together. But yeah, they take on this particular form, and one can so if you linearize this, if you linearize about ADS3, so these are of course nonlinear equations, but if you linearize about a background, ADS3 background like E bar mu A, you get the Fronsdal equations. So this is a little bit of tedious algebra, but this was showed by Campoglioni and collaborators a few years ago, that you indeed recover the Fronsdal equations from the linearized version of these, because you can solve for the spin connection and the right equations for phi. Yeah.
Excuse me. So, what about the component that's not totally symmetrized with the one-form index?
Sorry, which one?
I mean, you are symmetrizing the one-form index together with the other indices.
Where? Here?
When you to find phi.
Well, actually, I needn't have put this in because this is actually becomes symmetric because this is actually symmetric.
Right.
And therefore this is symmetrized, and therefore you get the mu1 to mu s minus 1. This piece becomes this becomes automatically symmetrized.
Mu, but you also have a one-form index, right?
Yeah, mu s. So that also you can. So there is no propagating degree of freedom associated. So you're thinking of this box, something like this.
Right.
There is no propagating degree of freedom associated with that. Yeah. So there's only the symmetric one which has some. So one thing I want to stress is that this frame formulation is what generalizes into the higher dimensional case for the Vassiliev. So this is all this seems relatively simple because it is Chern-Simon's theory, and these are finite n by n matrices and so on. The generic case of Vassiliev is more complicated, but it is along very similar lines, and the full Vassiliev theory is also expressed in the frame formulation rather than in the original metric or Fronsdal-like formulation. So even now, no one knows how to write down in this formulation in terms of the metric fields, in terms of coordinate indices. What is the full nonlinear gauge transformation? What is the what are the equations of motion, etc. Beyond the linearized level. So it becomes difficult to explicitly to eliminate all the omegas and write something purely in terms of these phi's. I did it here. This was all linearized about an ADS3 background, but if you are not if you want the full nonlinear case, then you obviously wanted to write it in some background independent way, and you can make some sort of so you can sort of assume that phi mu1 to mu s is say some trace of e mu1 to e mu s. So that's another way to write the full nonlinear case as that this phi mu1 to mu s is basically the trace of this. Then if you linearize this, you get this. This is the full SLNR. So this is a background independent sort of natural proposal for what this phi mu1 to mu s will be, to which of course it reduces to this at the linearized level. Yeah, so, but you don't know how to write down the full equations, the nonlinear equations of motion even for this. People have done it only order by order, but we still don't have a metric formulation which is fully nonlinear, even in 3 dimensions, which is the simplest. Okay, so that's about the equations of motion and the kinematics and the dynamics of these theories. I just want to say a little bit about the solutions that one has, the non-trivial solutions. So once again, to solve them, of course, you can try to look, so just like in the SL2R case, I had parameterized the most general solution in terms of the most general asymptotically ADS3 solution in terms of one function, holomorphic function, and one anti-holomorphic function. One can do something similar, so one finds that the So this is again of the form A is equal to some precisely in a similar form to before. Where B is so you can put it in a similar form as before, but now, of course, these are not SL2R elements; they are elements of SLNR, and the requirement that they are flat connections or solve these equations of motion tell you that this A must be of the form. Of course, you would recover the earlier set of solutions like this, but now you can have another function and similarly so these were the levels of the Chern-Simons theory. So you get two more. Oh, sorry, this is W. Where these are specific combinations of the TAB. Just like you remember, I defined L0L plus minus 1 as specific combinations of the JAs. Similarly, you can define these W's, which is sort of just, again, a basis change. If you define T00 as 1/4 W2 plus W minus 2 plus 2W0. So we are now looking, sorry, I should have said, let me specialize to the SL3R case. So the first case, which has a non-trivial, so the spin 3, so you have S equal to 2 and 3. So there are two, so these are all SL3R gauge fields. And so you have your JAs, and then you have the TAB, and the TAB you can write in just, there's T00, T01, T02, and T11, T22, and T12. You can express these in terms of, you can trade these for, there are expressions for these in terms of these generators W. Just write it down so that. So I told you how to construct these T's earlier in terms of the J's. I'd written down the explicit expression, so you can you can do the same thing and write expressions for these W matrices generators. These are more convenient. Because there are there are 5 independent generators, and those are W0, W plus minus 1, and W plus minus 2. And so the 5 independent generators at spin 3. So remember, there are 3 L0s. So L0, L plus minus 1 are the 3 generators of the SL2R, and then the additional 5 generators are W plus minus 1, W plus minus 2. So totally 8 generators, which is what the number of independent generators at SL3R are. So in terms of these generators, there's a specific form, there's a convenient form you can write these flat connections in, and they are parameterized by, again, one new function, which one can view as the sort of the generalization of the spin 2. So this was, so these corresponded to, from the boundary point of view, this was the stress tensor, and from here again, from holographic point of view, these correspond to spin 3 currents, as one can show by sort of explicit calculation. So these are, yeah, so expectation values. For a spin 3 current on the boundary. So this was the stress tensor, the spin 2 current, and this was this corresponds to conserved current on the boundary, which is a spin 3 current. Remember I mentioned right at in my first lecture that gauge fields in the bulk, spin S gauge fields in the bulk correspond to spin S conserved currents on the boundary. So this is a particular instance of that. So the general solution, flat connection, can be parameterized in this form, and you can generalize this to the spin to the SLNR case. I mean, it's just more notation, but so you can write down the general class, and there is one arbitrary function for every spin. So we had in the spin 3 case, we got one new function. If you go to the SL4 case, there'll be one more additional function, which will correspond to the spin 4 conserved current. So there'll be a higher and higher number of these additional currents or these additional functions which parameterize the general solution, asymptotically ADS solutions of this theory. But if you want to find something like black hole solutions, like we saw, so you can see that now you have a larger set of solutions than we had in the pure gravity case. So the pure gravity case is, of course, those solutions will continue to be solutions. You can always set this function to 0, and you will have all the solutions that you earlier had. So remember, I gave you the explicit forms for L and L bar for the BTZ black hole. They were parameterized by mass and an angular momentum. So you will continue to have all those solutions. So those are there, but now we have additional solutions, and we can ask what kind of black holes, whether there are new additional black holes which carry spin 3 charge, and indeed there are. And one can find, so there are, in fact, not just black hole solutions, there are a variety of other solutions as well, but you want to make sure they are regular, and once again, the condition for regularity is, it can be phrased in terms of the holonomy. So the regular solutions are, so they actually are of two kinds. There are what can call conical defects.